Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Today we are discussing molecular orbital theory in chemical bonding. More about MOT, that is molecular orbital theory in chemical bonding. It's a very important topic. So now I'm discussing that molecular orbital theory. Let us start now. Feeling with a little bit cold. So this is lecture number 6, chemical bonding, molecular orbital theory. So types of molecular orbitals. So what are the different types of molecular orbitals we have? Molecular orbitals of diatomic molecules are of two types: sigma molecular orbital and pi molecular orbital. Yes. So molecular orbital using spotlight now. As you can see here. So types of molecular orbitals. Molecular orbitals of diatomic molecules are of two types: sigma molecular orbital, pi molecular orbital. What is sigma molecular orbital, pi molecular orbital? As I already discussed, when atoms combines to form molecules. In the same way, electrons of two atoms combines together to form molecular orbital. Molecular orbital. In that molecular orbital, there are two types of diatomic molecules. Diatomic is like fluorine, hydrogen, chlorine, etc. Sigma molecular orbital and pi molecular orbital. So what is sigma molecular orbital? Sigma molecular orbitals are formed by the combination of atomic orbital along the molecular axis. You can see here. So these are nothing but along the molecular axis. Sigma molecular orbitals are formed by the combination of atomic orbitals along the molecular axis. The sigma molecular orbitals are symmetrical about the molecular axis. About the molecular axis, sigma molecular orbitals may or may not have a nodal plane. Sigma molecular orbitals may or may not have a nodal plane. From this, you'll get application topic differently. But here, as it is important for discussion, so we are discussing it. So what is sigma molecular orbitals? They are formed by the combination of atomic orbitals along the molecular axis. Next, what is pi molecular orbital? Pi molecular orbitals are formed by the combination of atomic orbitals perpendicular to the molecular axis. So these are perpendicular to the molecular axis. The pi molecular orbitals are not symmetrical. Pi molecular orbital will have at least one nodal plane. Since z-axis is considered to be molecular axis, 2pz orbitals will participate in sigma molecular orbital formation, and 2px and 2py orbitals participate in pi molecular orbital formation. So 2pz is only for sigma, and 2px and 2py, that is in orbitals and p orbitals, 2px, 2py, 2pz. So out of 2py and 2px and 2py, they participate in pi molecular orbital formation, whereas 2pz participate only in sigma molecular orbital. This is very important. So 2pz molecular, 2pz orbitals will participate only in sigma molecular orbital. Based on this only, formation of different types of molecular orbitals. First, in hydrogen atom, two 1s orbitals can combine to form sigma 1s bonding molecular orbital and sigma star 1s antibonding molecular orbitals. This can be represented as shown below. So, SS overlapping of first hydrogen atom, second hydrogen atom. One will be addition, one will be subtraction, as I already discussed. Addition will be bonding and subtraction will be antibonding. So, antibonding node here will be like this and bonding will be adding. So, in hydrogen atoms, two 1s orbital combine to form one sigma 1s bonding molecular orbital and sigma star 1s anti-bonding molecular orbitals. This can be represented as shown below. So it can combine to form sigma 1s bonding molecular orbital and sigma star 1s anti-bonding molecular orbitals. This can be represented as shown below. So in subtraction, it will leads to anti-bonding molecular orbital sigma star 1s, and by adding it, it leads to bonding molecular orbital. PP overlapping. 2pz overlaps 2pz orbitals of two bonding atoms combine to form sigma 2pz, as I told you before only. So whenever 2pz orbitals overlap with each other, of two atoms. They combine to form sigma 2pz bonding and sigma star 2pz anti-bonding. So they form sigma bonds only, and sigma star. Sigma means bonding and sigma star means anti-bonding molecular orbitals. This is illustrated in the following diagram. So whenever 2pz overlapping takes place, orbital overlapping, that is called pp overlapping. Here this is called end-to-end. Since it is end-to-end, it leads to the formation of sigma bond and sigma 2p and sigma star 2p. Although 2px, 2p orbitals of two bonding atoms combine to form pi molecular orbitals, pi 2px, pi star 2px, pi 2py, pi star 2py. Let us see the following diagram. See, this is not end to end, this is sidewise. Sidewise overlapping leads to the formation of pi bonds, pi 2px, pi star 2px. Similarly, pi 2py, pi star 2py. Now, here it's from here it is very, very important because they'll definitely ask in examination, write the molecular orbital configuration of different atoms. The order of energy of various molecular orbitals of homonuclear diatomic molecules up to nitrogen, including nitrogen, is given by sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. This is less than pi 2px, where is equal to, these two are equal because they are nothing but degenerate. Sigma 2pz, pi star 2px is equal to pi star 2p antibonding. These are also equal to means same, and sigma star 2pz. So how will you apply this configuration? This is nothing but molecular orbital configuration. Molecular orbital configuration. Let us see, for example, we'll write for nitrogen. Just making it clear. Let us see for nitrogen. Nitrogen. So nitrogen atomic number is 7. So two nitrogens. So first we have 1s2, 2s2, 2p3. And first nitrogen. Second nitrogen also 1s2, 2s2, 2p3. Total there are 14 electrons. In nitrogen molecule there are for total 14 electrons. So till 14 we have to fill up like this. So for example, each molecular orbital contains maximum 2 electrons, we already know. So the configuration for nitrogen molecule will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, because SS overlapping leads to only bonding and antibonding sigma bonds. And pi 2px2, here how much it is total already? 2, 4, 6, 8. Pi 2px2 is equal to pi 2py2. So already till here it is up to 10. How many will become over? 2, 4, 6, 8, 10, 12. 12 electrons are all over. Next we have sigma 2pz. So total 14 electron configuration. This is the configuration of nitrogen molecular orbital. Sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2, pi, this is called pi 2px2, pi 2py2, sigma 2pz2. So this is the configuration of nitrogen molecule as it has 14 electrons. Together, two nitrogen atoms has 14 electrons. So some will be going for bonding, some will be going for, and following this pattern. This is the pattern for finding homonuclear. The order of energy of various molecular orbitals of homonuclear diatomic molecules up to nitrogen, including nitrogen. Up to nitrogen means even we can write it for carbon and beryllium, boron, helium, hydrogen, etc. So up to here it is like this. So I hope it is clear. So from this we can also find bond orders also. So next. Similarly, the order of energy of molecular orbitals of homonuclear diatomic molecules from oxygen onwards is given by, from oxygen onwards means after oxygen flow in neon. We have to follow this because maximum we can fill up 20 electrons because 2, 4, 6, 8, 10, 12, 16, 8, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Maximum for 20 electrons only we have this type of molecular orbital diagrams. That too for homonuclear diatomic molecules. And for oxygen, we have to use this order. That order is different. Here, sigma 1 is sigma star 1 is sigma 2 is sigma star 2 is. Till here it is same. Sigma 2pz also same. Pi 2px, pi 2py is also same. Pi star 2px, pi star 2py, and sigma star 2pz. This is the order. Sigma star 2pz. Sigma 2pz and sigma star 2pz. Sigma 2pz will come front. Whereas in the previous case, if you see, it will come last. So sigma 2pz after pi 2px 2py we will get sigma 2pz. But here just pi 2px pi 2pi after sigma 2pz. This is the format for oxygen molecule. So let us write for oxygen molecule configuration. Oxygen, let us write for oxygen molecule. Oxygen molecule contains how many electrons? 16 electrons. So 16 electrons because oxygen atom contains 8 electrons. 8 plus 8, 16. Two oxygen atoms combined to form oxygen molecule. So the configuration for oxygen molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. After sigma star, we have sigma 2pz, sigma 2pz2, pi 2px2 is equal to pi 2py2. So total here, how many electrons totally filled? 2, 4, 6, 8, 10, 12, 14. Still we have two more electrons. Since it is degenerate orbital, pi star 2px2, 2px2 will not come because only two electrons left. So pi star 2px1, pi star 2py1. So in this way, right, this is the configuration of pi star 2px1, pi star 2p1. This is the configuration of oxygen molecule, molecular orbital configuration of oxygen. So this is clear. I hope it is clear now. So this is very, very important. Molecular orbital configurations are very important. They'll ask definitely one question for competitive exams. The distribution of electrons in various molecular orbitals is known as electronic configuration of molecule. From the electronic configuration of molecules, we can understand about the stability of the molecule and also magnetic property of the molecule. How can we say magnetic property? Suppose if the molecule has unpaired electrons, then it is paramagnetic. If the molecule has no unpaired electrons, then it is diamagnetic in nature. So paramagnetic and diamagnetic. So by this we can write by the electronic configuration of molecules of a molecule. From the electronic configuration of molecules, we can understand about the stability of the molecule as well as magnetic property of the molecule also. Let the number of electrons in bonding molecular orbitals. So how to find stability of molecules? Very, very important. You can just see here. Let the number of electrons in bonding molecular orbital will be Nb. Nb means number of electrons in bonding molecular orbital. And the number of electrons in anti-bonding orbitals is Na. If the number of electrons in bonding molecular orbital is higher than that of anti-bonding molecular orbital, the molecule is more stable. And the molecule is unstable if the number of electrons in ABMO is more than as in BMO. Means as I told you, if the number of electrons in anti-bonding molecular orbitals are more than electrons in bonding molecular orbitals, because it is not possible, the molecule is unstable. And in reality, there is no molecule unstable. There is no molecule unstable. So all the molecules are stable. Almost all the molecules are stable. So let the number of electrons. So the number of electrons in BMO, that is bonding molecular orbital, is Nb, and the number of electrons in anti-bonding molecular orbital is Na. If the number of electrons in bonding molecular orbitals is higher than that of ABMO, that is anti-bonding molecular orbitals, the molecule is more stable. So usually almost all the molecules are stable. Next, how to find bond order. This is also very, very important. They'll ask what is the bond order of nitrogen, oxygen, helium, neon, etc. Up to 20 electrons. So what is bond order? It is defined as a 1/2 of the difference between the number of electrons in bonding molecular orbital as well as in anti-bonding. So simple formula, bond order is equal to half into Nb minus Na. So let us take, if Nb is greater than Na, that is the bond order is positive, indicating the molecule is stable. If Na is less than Nb, the bond order is negative. The molecule is unstable and cannot exist, as I told you. And if Na is equal to Nb, the bond order is 0, the molecule cannot exist. So there is no molecule which can exist with bond order 0. And usually the bond order is positive only, indicating the molecule is stable. If Na is less than Nb, automatically the bond order will become negative and the molecule is unstable and cannot exist. So all these points are very important. Now, so before going to this, I want to explain how to calculate bond order for nitrogen. Here, just you can just see here, for example, for nitrogen, oxygen, etc. So let us see in the case of nitrogen, how to find bond order. So I don't think here space is there. We just will see like later. Now I can write it here seriously. So nitrogen molecule contains how many electrons? How many electrons? 14 electrons. So let us find out the bond order for nitrogen. First, to find bond order, we should write the configuration. So configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2, sigma 2pz2. Total how many? 2, 4, 6, 8, 10, 12, 14. So this is the configuration. Now, bond order of nitrogen is equal to bond order of, to find bond order of nitrogen molecule is equal to 1 by 2 into N of B, number of bonding electrons in molecular orbitals, number of bonding, 2, only bonding I'm underlining, see here, this is bonding, 4, 6, 8, 10. Bonding means without star. So half into Nb minus Na, that is nothing but 1 by 2 into Nb is how much? Number of electrons in bonding? 2, 4, 6, 8, 10 electrons. So 10 minus number of electrons in antibonding. Antibonding we have 1, sorry, so it is 2 here and 2 here. Total 4. There is no other antibonding. So 10 minus 4. So 1 by 2 into 6. So it is 3. Therefore, nitrogen is N triple bond N. I hope it is clear now. So like this, you can find bond order for oxygen and any other molecule. So this is very, very important. Just copy down in your classwork. How to find bond order. That is the formula is half into NB. What is NB? Number of electrons in bonding molecular orbitals. Na is number of electrons in anti-bonding molecular orbitals. So bonding means without star. So sigma 1s2, sigma 2s2, pi 2px2, pi 2py2, sigma 2pz2. Nitrogen will follow this order. So bond order is equal to half into Nb minus Na. Anti-bonding sigma star 1s2, sigma star 2s. There is no other stars are there. So anti-bonding. So half into 10 minus 4 is equal to 3. That is N triple bond N. I hope it is clear now. So next we'll discuss. So bond order, we can discuss bond order. So already we discussed this is bond order. So if Nb is greater than Na, the bond order is positive, indicating the molecule is stable. And if Na is greater than Nb, the bond order is negative and the molecule is unstable and cannot exist. If Na is equal to Nb, the bond order is 0 and the molecule cannot exist. So next we see magnetic nature. A substance is said to be diamagnetic if it does not show any attraction towards applied magnetic field. The molecule will not have any unpaired electrons. So, in our knowledge, how can we say a substance is diamagnetic if it does not have any unpaired electrons? If it has unpaired electrons, it is said to be paramagnetic. A substance is said to be paramagnetic if it shows a weak attraction towards the applied magnetic field. This we cannot say because this we cannot see because and only in our view the substance will contain at least one or more unpaired electrons because applying magnetic field to the atom is not possible for us. Only by spectral studies only we can do it. But here this we can identify. If it contains no unpaired electrons, if it do not have no unpaired electrons, it is diamagnetic. If it has unpaired electrons, at least one or more unpaired electrons, it is paramagnetic. So paramagnetic will show weak attraction towards the applied magnetic field, and diamagnetic does not show any attraction towards the applied magnetic field. If all the electrons in the molecular orbitals are paired, then the molecule is diamagnetic in nature. If any molecular orbital contains unpaired electron, the molecule shows parametric behavior. So now let us see which type of molecule will show parametric behavior. Hydrogen molecule. Let us see. Hydrogen molecule is formed by the combination of 1s orbital of two hydrogen atoms because hydrogen molecule itself containing two electrons. The two orbitals combine to form two molecular orbitals, and one will be bonding molecular orbital and the other will be anti-bonding molecular orbital. So the two electrons are occupied in BMO only because of the pattern. If you see the pattern, so it has only two electrons. So it is nothing but what? Only sigma 1s2. Only sigma 1s2 means here what happens, the electrons will be in bonding only. There is no electrons in anti-bonding. So the two orbitals combine to form molecular orbitals and one will be bonding molecular orbital, other will be anti-bonding. But the two electrons are occupied in BMO only. So the energy level of diagram is given by, so we can see the diagram. Let us see calculation of bond order. So you can see bond order. So bond order is equal to bond order for hydrogen molecule I'm writing here, and again afterwards I'll repeat it. So half into Nb minus Na. That is Nb is number of electrons in bonding 2 minus Na, no anti-bonding orbitals. So 1 by 2 into 2, it is equal to 1. So hydrogen is nothing but single covalent bond, H single covalent bond. So bond order is 1. Now this is the way you'll find bond order, but here our discussion is not bond order. Here applications of MOT in terms of for the formation of molecule. So here how to add the bond diagram. So oneness. So in sigma 1s only two electrons have been occupied, and sigma star 1 is no. So that's why it is kept empty. So this is the energy level diagram. Energy level diagram for the molecular orbital. Now the bond order of hydrogen is calculated as follows. Already this we have done. It is equal to 1. This implies that hydrogen molecule has the two atoms are bonded by single covalent bond because bond order is 1. Also hydrogen shows diametric behavior as there are no unpaired electrons because sigma 1 is 2. Sigma star 1 is 0. So all are paired here. Paired means here molecule it is diametric in behavior. There are no unpaired electrons. So I hope it is clear. So how to calculate bond order and how to identify whether it contains unpaired electrons or not. If it contains unpaired electrons, we'll say it is diamagnetic. If it does not contain unpaired electrons, it is we'll say it is diamagnetic in nature. Diamagnetic in nature. Next, lithium molecule. Let us see for lithium molecule. The electronic configuration of lithium is 1s2 2s1. Two lithium atoms combine to form lithium molecule, as already we know. So total there are total how many electrons? 6 electrons. So the 1s orbital with 1s orbital and 2s orbital combine with 2s orbitals only to form molecular orbitals. So simply you can say right for instead of seeing all those things, you can write directly for 6 electrons. So 6 electrons means you can write like this up to lithium. Sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, and sigma star 2 is 2 no electrons because only 6 electrons. So for lithium, molecular orbital configuration for lithium molecule. So if you see like this, simply 1s, and 2s also. Next, how to draw the diagram for this? And just right here, energy level diagram. Simply sigma 1 is 2, sigma star 1 is 2, sigma 1 minute, sigma 1 is 2. So sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is no electron. And these two electrons you have to write like this. One upward, one downward. One upward means here one and one upward. What will say? Only sigma 1 is 2. Downward will say sigma star 1 is 2. And upward only here you see. You can see the difference. Upward have sigma 2 is 2 only. If you have sigma star 2 is 2, then you'll get downward arrow here, downward arrow here. So only upward arrows in the side indicate sigma s orbital and downward arrow indicates sigma star s orbitals. I hope it is clear. Next. So bond order of lithium, as we can find, sigma 1 is to sigma star 1 is sigma 2 is to total electrons in bonding. So you can write that the molecular orbital configuration sigma 1 is to sigma star 1 is to sigma 2 is to sigma star 2 is to 2s0, it is no electron. So total bonding electrons 2 plus 2, 4. So 4 here we have written. Anti-bonding electrons 2 minus 2 by 2 is equal to 1. So the two lithium atoms are bonded by single covalent bond. The lithium molecule is diamagnetic substance as there are no unpaired electrons because all are completely filled electrons. So the molecular orbital configuration of lithium molecule is sigma 1 is to sigma star 1 is to sigma 2 is to sigma star 2 is. So I hope it is clear. So the molecular orbital configuration is also represented as Kk sigma 2 is 2 where Kk represents the K shell is completely filled up. So K shell means K2 L8 like that. So Kk also you can Kk means sigma 1 is to sigma star 1 is 2 in the molecule. Kk means what? Sigma 1 is to sigma star 1 is 2. Sigma 1 is to sigma star 1 is 2. Instead of writing sigma 1 is to sigma star 1 is 2, you can write Kk sigma 2 is 2. After that, what you have? Sigma star 2 is 2. Kk means like this. So I hope it is clear. Next, helium molecule. Let us see. The electron configuration in helium is 1 is 2. Already we know. The total number of electrons in helium molecule is 4. The energy level diagram, we can write sigma 1 is to sigma star 1 is 2. Simple. 1 is to 2. So this is the energy level diagram. Because helium contains 4 electrons, helium molecule contains 4 electrons. 2 will be in bonding and 2 will be in anti-bonding. So bonding, bonding, anti-bonding, anti-bonding. So I hope it is clear. So now let us see how to calculate bond order. So 2 minus 2 by 0. 0. That's why helium molecule does not exist. Since the bond order of helium molecule is 0, it is highly unstable. It cannot exist. That's why helium is. Helium is monoatomic molecule. Helium is monoatomic. Monoatomic means only one atom in its molecule. Monoatomic molecule, very very important. So helium is monoatomic molecule. The molecule can hence the noble gases are monoatomic gases and no bond is found between the noble gas atoms. Since they are monoatomic, there is no bond found between them. So that's why how we got zero, bond order 0, you already understood. Next. So this is the way to write molecular orbital theory. Next we have next topic in this chapter. We are continuing now. Next concept in this chapter. So how to write molecular orbital configuration. I think you understood. Next. So application of MOT for homonuclear diatomic molecules, carbon molecule. Let us see C2. Homonuclear. Homonuclear means similar atoms. So the electron configuration of carbon is 1s to 2s to 2p2 as we already know. So for two carbon atoms, there are total how many electrons? How many electrons? There are total 12 electrons, which need to be filled up in molecular orbitals. The KK shell is completely filled and the energy level diagram for 2s and 2p orbitals is as shown figure. Now you can see the diagram. So in this way, total 12 electrons, sigma 1s2, sigma star 1s2, that is Kk is completely filled up. So here I'm writing Kk is completely filled up. Kk means first level, Kk is filled up. So after Kk, we have sigma 2s2, sigma star 2s2, pi 2p y1, pi 2px1, pi 2px2, pi 2py2. Total, how many? Total we have 12 electrons. So after that, we don't have pi star 2px1, pi star 2py1. So sigma star 2pz, sigma 2pz. So there are no electrons in this because total it is 12 only. So till already we have 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 up to here only it is over. So pi 2px, pi 2px. Just configuration. Just I'm writing the configuration if you want, you can see here. So here sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, that is antibonding, pi 2px2, and pi 2py2. So pi 2px2, pi 2py2. So pi 2px2, pi 2py2, here 2px, 2py, 2 electrons. Total 1, 2, 4, 6, 8, 10, 12 electrons. So 12 electrons already over. So this will be left empty because of no electrons present in carbon molecule. So I hope it is clear. Let us see now how to find bond order. So the molecular orbital configuration Kk means sigma 1 is to sigma star 1 is to, that is K shell is completely filled. Sigma 2s to sigma star 2s to pi 2px to pi 2pi2. This is the molecular configuration of carbon molecule. Since there are no unpaired electrons in the molecule, the carbon molecule is diametric in nature because all are completely filled in. The bond order of C2 is equal to Nb minus Na by 2, 6 minus 2 by 2, it is equal to 2. The two carbon atoms are held together by double bond. So, two carbon atoms, since the bond order is equal to, the two carbon atoms are held together by C double bond C. The molecules of C2 is found in vapor phase only, and the double bond is made up of by two pi bonds as the bonding electrons are present in pi molecular orbitals. I hope it is clear. So, since the bond, how to find bond order also we know, we have discussed all these things. Next. Nitrogen molecule, very interesting. So nitrogen already have shown you. Total 14 electrons in nitrogen molecule. The energy level diagram of nitrogen is shown below. So sigma 2h to sigma star 2h to pi 2px to pi 2py2 sigma 2pz2 up to sigma 2pz2 only will get because total 14 electrons. After kk sigma 1s to sigma 2s2 also after kk. That is case shape. So bond order is here also all are filled up. So bond order is Nb minus Na by 2, that is 8 minus 2 by 2 is equal to 3. So the nitrogen, two nitrogen atoms are held together by triple bond. Out of this one is sigma bond and the other two are pi bonds because triple bond means one sigma bond, one pi bond. As there are no unpaired electrons in nitrogen molecule, it is also showing a diametric behavior. Because of the configuration, you can see all are completely filled. So that's why it is also diametric in nature. Next, we'll see oxygen molecule. The electron configuration of oxygen is 1s2 2s2p4. So two oxygen atoms means total 16 electrons. You can see here how many electrons total? 16 electrons are present in which should be filled in molecular orbitals. 4 electrons are already filled in KK shell. In the energy level diagram of oxygen, the sigma 2pz orbital have lesser energy than the pi 2px or pi 2p. Only from oxygen onwards the pattern will change because the sigma 2pz have lesser energy than the pi 2px and pi 2py. So that's why sigma 2pz will come first. Whereas if you see in the case of nitrogen, pi 2px, pi 2py after sigma 2pz will come. But in the case of oxygen, first sigma 2pz will come afterwards. We have pi 2px, pi 2py. That is the only change in order. Remaining all the same. The energy level diagram of the oxygen is as shown below. So what is the energy level diagram of oxygen? You can see here. See here, sigma 2s, sigma star 2s. Afterwards, we have sigma 2pz. Actually, before that, what we have pi 2px, pi 2p and up to nitrogen. But in oxygen case, it is observed that sigma 2pz is lesser energy than pi 2px and pi 2py. So sigma 2pz will come first. After that, pi 2px, pi 2py, and pi star 2px1, pi star 2p1. This is very important. Two electrons cannot accommodate. First, they will feel bonding. Afterwards, they will feel anti-bonding. So here also upward arrow, then downward arrow, downward arrow. So only two electrons is left because total 16. Already 4 is KK, then 6, 8, 10, 12, 14, 16. So total 16. So for sigma star 2pz, no electrons. And pi star 2px1, pi star 2py1. Because they are degenerate. Degenerate means is equal to same equivalent levels. So one electron will fill in X, one electron will fill in Y. But not two electrons in X only. I hope it is clear. So this is the energy level diagram. And let us see configuration. The pi star 2px and pi star 2py antibonding orbitals have only one unpaired electron each. Hence the oxygen molecule is diametric in nature. No, it is unpaired electron we have. They have one unpaired electron, so it is not diametric in nature. It is, but BBT could not explain the paramagnetic nature of oxygen, which is successfully explained by MOT. So that's what BBT could not explain the paramagnetic nature of oxygen, but here the oxygen molecule is done diamagnetic, it is paramagnetic in nature. Here it is printed wrong. Let's change it. It is not diamagnetic because it has one unpaired electron. It is paramagnetic. So nitrogen is diamagnetic molecule, but oxygen molecule is paramagnetic. Sorry. So the bond order of oxygen molecule is Nb minus Na by 2. It is equal to 2. I hope it is clear. Very simple to understand. Next. Thus, in oxygen molecule, the two oxygen atoms are bonded by double bond, in which include one sigma bond and one pi bond. Since already we know oxygen has double bond because the bond order is two oxygen O double bond O. So double bonds we have one sigma bond and one pi bond. This already we know. How to find number of sigma bonds and pi bonds we have already discussed. This is the configuration of oxygen. Only for oxygen we have the difference sigma 2pz will come first. Next topic, last topic in this chapter, that is called hydrogen bonding. So what is hydrogen bonding? When hydrogen atom is bonded to more electronegative atoms like fluorine, oxygen, and nitrogen. Very important. When hydrogen atom is bonded to more electronegative atoms like fluorine, oxygen, and nitrogen. The bond pair of electrons, the bonded pair of electrons are attracted towards the more electronegative atom. Hence, the hydrogen atom gets a partial positive charge because hydrogen loses one electron and partial positive charge, and the electronegative atom gets a partial negative charge. This partially charged hydrogen gets attracted by an electronegative atom belonging to either same molecule or different molecule. So that is called hydrogen bonding. In simple words, you can say hydrogen attracted to similar hydrogen. This weak attraction between the positively charged hydrogen and the electronegative atom is known as hydrogen bond. Hydrogen bond just a moment. Hydrogen bond is defined as the attractive forces which binds the hydrogen atom of one molecule with hydrogen high electronegative atom of another molecule or within the same molecule. So we have hydrogen bonding in HF and water can be shown as in the diagram. We can see here. See, the hydrogen of this atom, this molecule, hydrogen fluoride, is attracted towards fluorine. So these dotted lines represent hydrogen bonding exists. So what is that lines? Dotted lines, like this dotted lines. They exist a bond between hydrogen, fluorine, hydrogen, fluorine, hydrogen. So in water also. So hydrogen attached to oxygen atom is in an attraction with oxygen of second water molecule. This hydrogen again, second of water molecule. Hydrogen again, water molecule, oxygen molecule. So I hope it is clear. And hydrogen bond is represented by dotted. And due to the presence of hydrogen bonding only, the boiling points of water is high, that is 100 degrees C. Because in water we have boiling point of water is high because we have in water hydrogen bonding is there. So water molecules, so many water molecules will fuse together, will combine together to form a hydrogen, say, by the means of hydrogen bonding only. So this is the hydrogen bonding in water. So one of the main consequence of hydrogen bonding is hydrogen bonding is more water. Next, hydrogen bond can take place in two steps. One is intermolecular hydrogen bonding, and there is intramolecular hydrogen bonding. Very important. Intermolecular means between, intra means within. I'll write here simple to understand. Inter means between two molecules. Intra means within the molecule. Intra means between the molecule, and inter means between the molecules. So what is intermolecular and intermolecular hydrogen bonding? We are going to discuss now. If the hydrogen bond takes place between hydrogen atom of one molecule and the electronegative atom of another molecule. See here, hydrogen atom of one molecule and the electronegative atom of another molecule, like in the case of water we have seen. Then the hydrogen bond is known as intermolecular hydrogen bonding. The hydrogen bonding in water, hydrogen fluoride is examples of intermolecular hydrogen bonding. So intermolecular hydrogen bonding is, for example, in water, if we take into consideration, so OH H is the water diagram, means water structure. So if this is in contact with oxygen, hydrogen, hydrogen. So this hydrogen is in attraction with another oxygen of another molecule, not the same molecule, another molecule. So hydrogen atom of one molecule and the electronegative atom of another molecule. Electronegative means here oxygen. And then the hydrogen bond is known as intermolecular hydrogen bonding, and they are represented by dotted lines. These are called dotted lines. So example HF and H. So this type of bonding HF and water. So this is called intermolecular hydrogen bonding. What is this called? Intermolecular hydrogen bonding. Very easy to understand. I hope it is clear. Next, intramolecular. So if the hydrogen bond takes place between the hydrogen atom of one molecule and the electronegative atom of in the same molecule is more important. Then the hydrogen bond is known as intramolecular hydrogen bonding. So same molecule means if the hydrogen atom is in attraction with electronegative atom in the same molecule is important. We'll call it as intramolecular hydrogen bonding. Example, orthonitrophenol. So what is orthonitrophenol? We'll see now. See here. O-nitrophenol. O-nitrophenol means phenol means OH, nitro means NO2. So the hydrogen is in intermolecular bonding with oxygen, electronegative atom of another same molecule, but same molecule with the same molecule, but it is electronegative atom of the molecule. So this is called intramolecular hydrogen bonding. Intramolecular hydrogen bonding. I hope it is clear. So this is called intramolecular hydrogen bonding. Next examples now. Among N2H4, N2, N2O4, and N2O, in which molecule NN bond length is shortest? The basic idea is bond length is shortest means here bond length is proportional to 1 by bond order. Simple words. Means if bond order is more, bond length is less. Bond length is proportional to 1 by bond order. Also, we can write bond length is proportional to 1 by bond strength. Bond length is proportional to, just note down this 1 by bond strength. So either bond strength we can compare, that is strength of the bond, or bond enthalpy, or bond order we can compare, and one more is there. Bond length, bond order is proportional to, since these are equal, so we can say bond order is proportional to bond enthalpy. So bond order is proportional to bond enthalpy. Bond length is proportional to 1 by bond. Bond length is proportional to 1 by bond strength. So based on this, we can say nitrogen molecule bond order is 3. So N2H4. In which molecule NN bond length is shortest? Shortest means highest bond energy, shortest bond length. So I hope it could be nitrogen molecule because its bond order is 3. As I told you, highest bond order. So highest bond order, it has highest bond order. So highest bond order means it is nothing but least bond length because N triple bond N is highest bond order. I hope it is clear. Next I'm sharing new slides. Continuation of the topic. So more about this we'll do now. Next topic. Already it's over. Just we have a recap of this continuation. So determination of hybridization of the central atom, the shape of molecule already we know. So H is equal to half into V plus M minus C plus C. This formula we discussed already in the previous lecture. So where H is equal to number of orbitals involved in hybridization, V is called number of valence electrons of central atom, M is equal to this hybridization formula we can use for not only for finding hybridization for molecules, we can find for ions also, ionic species. Ionic species means, for example, like SO4 2 minus, SO4 2 minus. So how to find hybridization for SO4 2 minus? We can take, writing it clear again. So for SO4 2 minus, how to find hybridization for SO4 2 minus? You can see here. So half into hybridization H is equal to 1 by 2 into number of valence electrons, number of orbitals involved in hybridization. So that is number of valence electrons of central atom, sulfur, central atom is 6. And number of monovalent atoms linked with central atom. Here, 4 oxygen atoms are linked with central atom sulfur, but oxygen is not monovalent, so minus 0. Plus number of cations, there is no cations, so minus 0. Sorry, this is plus 0. And here, 6 plus 0 minus 0 because no cations plus how many anions? 2. Only number we have to write, not the sign for anion. So 2. 8 by 2. 8 by 2 means 4. 4 means sp3 hybridization. What hybridization? sp3. So charge of cation where H is equal to number of orbitals involved in the hybridization. H is equal to 4 means sp3. I hope it is clear. In this you will find by using this formula. This already we discussed. This formula is useful for finding hybridization even for ions also. From the values of H, the hybridization of central atom can be predicted if H is equal to 2. As now in the previous session we have done H is equal to 4, it is sp3. H is equal to 5, sp3d, 6, sp3d2, 7, sp3d3, and 2, sp. Next, generally, a covalent bond is formed by sharing one pair of electrons between two atoms. However, in certain molecules, covalent bonds are observed to contain odd number of electrons. Such covalent bonds are known as odd electron bonds. These covalent bonds may contain one or three electrons. Examples: molecules having odd electron are NO, He2 plus, N2O, CO, etc. CO means total how many electrons? Carbon is 6 and oxygen is 8, 14 total. But it has odd electrons because the covalent bond is forming by sharing one pair of electrons between two atoms. So these are nothing but odd electrons. The odd electron bonds are found between like atoms or atoms with zero point 0.5 difference in electronegativity. The odd electron bonds are of lesser strength than normal covalent bonds. These molecules are highly reactive and tend to dimerize. Dimerize means they will form two, two molecules. Dimerize. Dimerize means, for example, AlCl3 does not exist because it is of odd electron molecule. It exists as Al2Cl6 dimer 2 times Al2Cl6. So this is called dimer. Again, I'm writing clear. So what is dimerize means? There are two molecules combined together. For example, Al aluminum chloride does not exist, whereas aluminum chloride exists as Al Al2Cl6. This is called dimerization. So that is called dimerization. So two molecules are held together. It is nothing but dimerize. Bond length of one electron bond is larger than normal covalent bond, while bond length of the electron bond is lesser than the normal covalent bond. Next, application of MOT is already we discussed for helium 2 plus molecule. He2 plus, this is existing. He2 plus molecule is obtained by the combination of He atom and helium plus ion, that is alpha particle like. So He2 plus ion. The total number of electrons in the molecule is 3. So this is nothing but odd electron molecule. Sigma 1 is to sigma star 1 is to. And the molecular ion is paramagnetic because it contains one unpaired electron due to the presence of one unpaired electron. So bond order is equal to number of electrons in bonding 2 minus anti-bonding 1 by 2, which is equal to 0.5. Next, H2 plus molecule bond order is 0.5. H2 plus means it contains two electrons, only one electron, because the H2 plus molecule is formed by the combination of hydrogen atom and H plus ion. So the total number of electrons in the system is only one because H2 plus, one electron is already lost. Actually, H2 means two electrons. H2 plus means one electron is already lost. So one electron, sigma 1 is 1. So bond order is 0.5 and it is also paramagnetic in nature. Paramagnetic in nature. Next, nitrogen molecule order. We know the molecular ions of nitrogen are N2 plus, N2, 2 plus, N2 plus. So N2 plus means out of 14 electrons, out of 14 for nitrogen molecule, one electron is lost. N2 2 plus means two electrons. So 14 minus 1, it is 13. Two electrons means 12. And N2 plus, the molecular configuration of N2 plus is 9 minus 4 by 2, that is 2.5. So that electron is also lost from sigma electron. Sigma electron. So magnetic nature is paramagnetic. So the molecular configuration of N2 plus is like this. It is diamagnetic, I believe, because it contains two, as I told you, diamagnetic. And the two electrons are going from sigma only. So whenever I'm writing here one more important point, whenever the molecule loses electron, if the molecule loses electron, it is from bonding molecular orbital only, as we have seen in these two cases, bonding molecular orbital, not from anti-bonding. So that's why here we got 8. Actually, we have 10 bonding electrons in nitrogen molecule, but here we have only 8 because of N2 2 plus. And the 2 electrons are removed from bonding only, not from anti-bonding. This you have to understand. So the stability of these molecules decreases with the increasing bond order. So bond order. So bond order for nitrogen it is 3. Very, very important. This type of question they'll ask. Bond order for nitrogen is how much? It is 3. N2 plus bond order is less than 3. N2 2 plus less than 2. So it is 2.5. So for example, I'll write here. From this only they'll ask question for the competitive exam. So it is 3, 2.5 and 2. So 3, 2.5 and 2. It means nothing but what? Here bond order highest, more the bond order, more is the stability. More the bond order, more is the stability. And with the addition of, with the loss of electrons, the bond order decreases. Very important. With the loss of electrons from the molecule, very important statement. The bond order decreases, because in examination we cannot find bond order, so much time it will take. So with this statement you can understand bond order also decreases as well as stability. So in the following in the decreasing order of bond order, increasing order of bond order. With the gain of electrons, bond order also increases. Let us see that also now. With the gain of electrons, bond order also increases. Now here you can see O2 plus, O2 2 plus, O2 minus, O2 2 minus. Let us see now. Here O2 plus means how many? Total for oxygen it is 16. 16 minus 1. Plus means 1 electron is lost. And that too from bonding molecular orbital. So 16 minus 1, 15. 15 means sigma 2s to sigma star 2s to sigma 2pz2 pi 2px2 pi 2py1 pi 2py2 pi star 2px1. And here anti-bonding pi star 2py1 is not there. So 1 electron is lost from anti-bonding. For oxygen, we are removing the electron from antibonding. O2 plus ion is obtained by removing 1 electron from antibonding molecular orbital. Very, very important, antibonding. So it is 2.5. So magnetic nature is paramagnetic. Now, molecular ions of oxygen, O2 2 plus, 2 electrons are removed. So 2 electrons are removed from 2 antibonding molecular orbitals. Then it is, this becomes 10 minus 4 by 2, it is 3. So magnetic nature is paramagnetic. So next coming to molecular ions of oxygen, O2 minus. O2 minus, the superoxide is obtained by adding 1 electron to anti-bonding molecular orbitals. Anti-bonding, we are adding 1 more electron. So the O2 minus is 1.5, magnetic nature paramagnetic. Next we have molecular ions of oxygen contain O2 2 minus peroxide. So bond order is 1. O2 2 minus. O2 2 means the electron is gaining. So and that too gaining for anti-bonding molecular orbitals by adding 2 electrons to anti-bonding. Very, very important, anti-bonding. So anti-bonding molecules are increasing. So in case of oxygen, for very, very important to note down, for nitrogen it is different, but in case of oxygen, addition of electrons, loss of electrons or addition of electrons will be from or to anti-bonding molecular orbitals only. Anti-bonding molecular ABM only. Very, very important. Due to which what happens? O2 2 minus is less than O2 minus is less than O2 plus is less than O2 2 plus. Because oxygen is 2. Already we know. O2 2 minus is 1. O2 2 minus is 1.5. So this is 1, 1.5, and this is 2.5, and this is 3. So our actual order is O2 2 minus less than O2 minus less than O2 less than O2 plus less than O2 2 plus. So I hope it is clear. So since for oxygen we have to do like this, a loss of electron or addition of electron will be from anti-bonding only. So the bond order will change and also the stability. And magnetic nature for O2 2 minus is diamagnetic and its bond order is 1. I hope it is clear. Next. Application of MOT for heteronuclear diatomic molecules. Heteronuclear means 2 nucleus, carbon monoxide. because carbon is having 6 electrons, oxygen is having, sorry, carbon is having 6, oxygen is having 8, total 14 electrons, 6 from carbon, 8 from oxygen. So the molecular configuration is similar to that of nitrogen molecule. Sigma 2 H2, sigma star 2 H2 like this. So we have bond order is the magnetic nature, diamagnetic. So just number of electrons follow the order. Order will be for nitrogen because less than 14. So if it is less than 14, so it is total, it is equal to 14 or less than 14, we have to follow nitrogen model. If it is more than 14, we have to follow oxygen model. That is nothing but simple. Sigma 2pz will come first, then pi 2px, then pi 2py. But here we are getting equal to 14, so we have to follow like nitrogen only. So the bond order is 3, and magnetic nature is paramagnetic, sorry, diamagnetic. Next. Nitric oxide molecule. Nitric oxide contains 15. 15 means I told you, no, sigma 2pz will come first. Sigma 2pz will come first. So sigma 2s to sigma star 2 to sigma 2pz to sigma 2px 2 pi. So above 14 we have to follow oxygen. Below 14, up to 14 we have to follow nitrogen. Above 14 we have to follow oxygen. 7 from nitrogen, 8 from oxygen. So the bond order is 2.5, as it contains unpaired electrons. Due to presence of unpaired electrons, it is diamagnetic. No, it is paramagnetic. Again, it is given wrong here. So it is paramagnetic in nature. I'm just changing it. You also can change. It is paramagnetic. So nitric oxide molecule is paramagnetic. Next. Cyanide ion. The total number of electrons in cyanide ion is 14. That is 6 from carbon, 7 from nitrogen, and 1 from negative charge because negative charge is there. So we have to follow nitrogen only. Sigma 2pz will be writing. So bond order is 3. Magnetic nature is diamagnetic. Let us see among CF4, CCl4, CH2, Cl2, and CSCl3, which is having maximum dipole moment. Dipole moment existing only for the electronegative and electropositive. So CHCl3, because it has carbon, I'll show you that CHCl3 dipole moment. Carbon, hydrogen, chlorine, chlorine, and chlorine. So there exists a dipole moment between this carbon and this chlorine, this carbon and this chlorine, this carbon and this chlorine. A similar dipole moment. So opposite dipoles cancel out, but this dipole moment is existing. So it's maximum. For CF4, if you take into consideration carbon, fluorine, 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 and fluorine. So carbon to fluorine, carbon to fluorine, carbon to fluorine, and carbon to fluorine. So opposite dipoles. This dipole gets cancelled. This dipole gets cancelled. So I hope it is clear. So answer is CSCl3. Next question. Copper to iodide is unstable even at ordinary temperature. Explain. This is not required here. Copper to iodine is not required here. So I'm ending this class. Ending this class. So I hope everything you understood. Thank you all. Thank you all.